In this video, we will take a look at the frequency domain representation of sinusoidal signals in VSS. Let's pick up where we left off in video 1.1. Here we have a sine block, generating a 1 MHz sinusoidal signal, connected to a swept variable that allows us to change the sampling rate using the tuner. We've determined that a sampling frequency of 100 MHz gives us a nice smooth waveform, so let's get rid of the swept variable here, and simply set the sampling frequency to 100 MHz directly on the sine block. Now, before we delve into the frequency domain representation of this signal, we must first change an important setting. Double-click on System Diagrams, select the RF Options tab, and then change the noise settings as shown, to remove all noise from our simulations. Now let's create a new graph, and add a power spectrum measurement to it. This may be found under System, Spectrum. Let's not change any of the default settings for now. As expected, we get a line spectrum with a single line located at 1 MHz. If we place a marker on it, we can see that the power associated with it is 10 milliwatts. But, hold on a minute, how can any power be dissipated when we have no resistive load in our diagram? That is because the simulator assumes that the sine block is terminated with a load equal to the characteristic impedance of the system, which, by default, is set to 50 ohm. We could use an actual load element in our diagram, and it is good practice to do so in general, but it wouldn't make a difference in this case. Indeed, if we calculate the power that our 1 volt peak sinusoidal signal would dissipate in a 50 ohm resistor, we get 10 milliwatts. We can also convert this value in dBm, which is the most widely used unit for spectrum analyzers. And in the measurement settings, there is a box that we can tick to use this unit for our plot. Note that the frequency axis stops at 50 MHz, because that is half of the 100 MHz sampling rate. By the Nyquist theorem, frequencies above half the sampling rate cannot be uniquely reconstructed, so VSS only displays the spectrum up to 50 MHz. Also note that we can view all of the automatically selected settings for our spectral plot by clicking the plot and holding down the left mouse button. When we lower the sampling rate to 20 MHz, the graph now only displays the spectrum up to 10 MHz. Press and hold on the plot to see how the automatic settings changed. Let's switch back to a 100 MHz sampling frequency and simply change the axis range in the usual way. Although we've zoomed in, the underlying acquisition settings are unchanged. For example, the resolution bandwidth has not decreased, so we do not obtain finer frequency resolution, only a magnified view. There is a more computationally efficient way to handle spectra in VSS, using complex envelope signals. We'll cover those in later videos. What we are going to do next is set up spectral measurements that align closely with the graphical representation of a Fourier series, the voltage spectrum for both amplitude and phase. Let's start with the amplitude spectrum. Let's create a new graph, then add a voltage spectrum measurement, Vspec. Make sure to select Magnitude under the complex modifier options. In this case, I'm going to manually set the resolution bandwidth to a reasonable value, 100 kHz, and set the video bandwidth to the same value. For now, I'll leave all the other settings unchanged, so we can see a more direct comparison of power and voltage spectra. As expected, the voltage spectrum shows a single component at 1 MHz with an amplitude of 1 volt. Working with voltage spectra also lets us examine the phase. Let's create a copy of the voltage spectrum graph, rename it, and change the setting of the Vspec measurement, so that spectrum type is set to threshold phase, and complex modifier to angle. Again, we have a single spectral component at 1 MHz. This is associated with a phase angle of -90 degrees, which matches the value we set in the sine block. Let's take a quick dive into the maths, so we can connect the theory you've learnt with what the simulator is showing and how it works. The Fourier series is often written as a constant term plus two separate summations, one with cosine terms, and one with sine terms. The arguments of these trigonometric functions contain the fundamental frequency for n equals 1, which I'll call f1 here, and its integer multiples for n greater than 1, known as harmonics. While this form is perfectly valid, it can feel a bit redundant, since sine and cosine are essentially the same function, differing only by a 90 degrees phase shift. A neater and more intuitive form of the Fourier series uses just one summation with cosine terms, but includes a phase shift inside the argument. By adjusting this phase, the cosine can represent a sine wave or any other trigonometric waveform we need. This also aligns well with how the sine element in VSS operates, as it actually generates a cosine function. In our current setup, we have set the phase of that sine block to -90 degrees, which produces a cosine with a -90 degrees phase shift, in other words, a sine function, and the phase spectrum confirms this. If we change the phase to 0 degrees, the amplitude of the single line in the phase spectrum reduces down to 0, indicating that we now have a pure cosine function. This is why I find the single summation notation more intuitive. Ultimately, we want to use the double-sided spectrum, which includes both positive and negative frequencies, to represent the voltage spectrum of our signal. The Fourier series expression that produces this spectrum uses complex coefficients, as shown here. While there are standard formulas for calculating these coefficients, for a simple cosine or sine waveform, I'll show you how the complex spectral components can be derived using Euler's formulas, along with a conceptual explanation of what negative frequencies actually represent. Let's start with a cosine signal of frequency f1, and a peak amplitude of 1 volt. This is exactly what our sine block is producing at the moment, since its phase is set to 0. Using Euler's formula, we can express this signal as the sum of two complex exponentials, a and b. In this equation, I've used the angular frequency omega to make the notation clearer. These exponentials represent two vectors of equal amplitude, 0.5 volts each, rotating in the complex plane. The first rotates at an angular frequency of omega 1 radians per second, or 1 megahertz, while the second rotates at -omega 1 radians per second, or -1 megahertz. The sign of the angular frequency simply indicates the direction of rotation. Positive omega corresponds to anticlockwise rotation, and negative omega corresponds to clockwise rotation. If we consider the resultant vector sum of these two rotating vectors over time, we obtain exactly the set of points needed to reconstruct our cosine function. So, if we go back to the equation for the complex Fourier series, by comparing the two sides term by term, we can see that both our C-1 and C1 coefficients have a magnitude of 0.5 and a phase of 0. Let's verify this in VSS. Let's open the settings for the voltage amplitude spectrum measurement and, under Frequencies Displayed, select All. As expected, we see two components, one at -1 MHz and one at 1 MHz, each with an amplitude of 0.5. We can do the same with the phase graph to show both negative and positive frequencies. And again, there are no surprises, each spectral component has a phase of 0 degrees. Let's now examine the sine waveform. Using Euler's formula and remembering that a sine is simply a cosine with a -90 degrees phase shift, we can write the equations shown here. Again, we have the sum of two rotating vectors, but in this case the one rotating at angular speed omega 1, i.e. anticlockwise, has an initial phase of -90 degrees, while the one rotating at -omega 1, i.e. clockwise, has an initial phase of 90 degrees. The resultant sum of these rotating vectors therefore produces a different set of points compared to the cosine case, and these points allow us to reconstruct a sine wave in the time domain. Now, if we go back to the equation for the complex Fourier series, by comparing the two sides of these equations, term by term, we can see that both our C-1 and C1 coefficients have a magnitude of 0.5, but the C-1 coefficient has phase of 90 degrees while the C1 coefficient has a phase of -90 degrees. Let's verify this in VSS. We simply change the phase parameter of our sine block to -90 degrees to generate a sine wave, and we can clearly see that the voltage amplitude spectrum remains unchanged. However, if we now examine the phase spectrum, we find that the -1 MHz component has a phase of 90 degrees, while the 1 MHz component has a phase of -90 degrees.